So in the last video, we talked a little bit about this idea of a mechanical battery and how it can be used to drive a current. In this video, we're going to really try to understand, well, how does that current actually show up, right? What is the underlying mechanism that causes the current to be driven around the circuit? And it's going to come down to this idea of the electric field, which exerts forces on charges, right? So going back to sort of our description of the electric force, if you have an electric field and you have a charge in the presence of an electric field, it is going to feel a push or a pull. And the direction of that push or pull will depend on the sign of the charge. So we can look at this circuit, which has our mechanical battery, and we can identify some pieces of it that tell us a little bit about what the electric field is going to look like. So if we're near this plate, right, the electric field is going to point away from that plate. And that kind of makes sense, right? So near this plate, we would expect electrons to be rushing onto the plate. So the force on those negatively charged electrons is going to be in the direction of the plate. Makes sense. On this side, the electric field is going to point towards the plate, right? And that also makes sense because the negatively charged electrons want to rush away from this negatively charged plate. So the force that they feel is going to be away from the plate. Now, everywhere in between, it's a little bit more of a complicated story because we might not be close enough to the ends of these plates or the ends of the battery to really experience an electric field that is associated with the battery itself. Now, it does produce an electric field, it's just that it could be quite small. But given this situation, we probably expect that the electric field associated with something in this picture here is going to act to drive the electrons around the circuit in this way. So we probably would expect that the electric field is going to be pointing sort of this way down here because the force on those electrons is going to be to the left and push them up. So if we keep tracking that around, we sort of expect the electric field to actually point opposite the motion of the electrons. Now, how does that actually happen? Well, the story is a little bit complicated in terms of how this gets set up. But it turns out that when you connect two ends of a wire like this, the charges that are actually on the wire, not the ones that are going to be moving around, but the charges that are on the wire sort of rearrange themselves in a way to produce an electric field in the wire that drives the current. And this rearrangement of the charge is called the surface charge. It's the charge that exists on the surface of the wire, and it generates an electric field that pushes the electrons that are actually part of the current along. And so what's going to happen is you're going to get a buildup of positive charge sort of near this side of the circuit, near the positive plate, and that'll get a little bit smaller as you get farther away from it. Eventually it will go to zero, and then you'll start actually having a buildup of electrons as you get closer to the negatively charged plate. Now, all of these charges exist on the surface of this wire, but what they do is they generate what we call a surface charge gradient. Right? And that surface charge gradient is actually what gives rise to the electric field in the wire. And it's that electric field that's in the wire that's a result of the surface charge gradient plus any electric field associated with the battery that drives this current around. Now, it turns out that that electric field under our steady state assumption is going to be a constant value. It'll be slightly different in different parts of the wire depending on the size of the wire and so forth. But for this wire where everything is the same thickness, this steady state assumption will give us that the electric field is going to be precisely the same everywhere throughout. Now, I know that sounds like magic, that we're like kind of sweeping something under the rug, but it turns out that if you go out and actually measure it, we have a demonstration on the course webpage that shows you that this surface charge gradient is actually real, and it does result in driving these electrons around. Now, in terms of the mathematics associated with this, what we need to do is sort of keep track of the current. And so what we're going to do is we're going to first define a thing that we're going to call the electron current, which is going to have this little I as its symbol. And it's basically just the number of electrons that pass any point per unit second. Now, this electron current, under our steady state assumption, is going to be a constant everywhere throughout every piece of the wire. Now, this electron current is also related to some properties of the wire itself and how those charges are actually moving. Now, we'll get into details on that in one of the next videos, but the idea is that this electron current has to do with the number density of charge carriers, that is, how many electrons are actually available to move around, how thick the wire is. The thicker the wire is, the bigger the electron current one can drive, and how fast, on average, those electrons are moving, because they don't actually move at the same speed as we're going to see in a moment, but there's some average velocity which they move with. So in fact, this is still going to give us the number of electrons passing a point per unit second. But this relates it to properties of the wire, namely how many electrons are available to actually move around, what is the size of the wire itself, and how fast are they moving around specifically. And we'll dig into this in a little bit. Now, the last thing to do is to relate this to something that you probably have some experience with, which is actually current, which we will call the conventional current. So the conventional current is the kind of current that you see when you're looking at different electronic components, when you're looking at stuff that you buy in the store, when you're looking at it coming out of the wall, right? This is the thing that's measured in amps, right? The number of charges, the amount of charge per unit time that passes a point. And it's related to the electron current through the sign of the charge carrier themselves. So this thing has units of coulombs per second, which we'll call an amp. So this is the thing that you're probably used to seeing, thinking about household items and so forth, right? And the reason that we sort of separate these two things is because charge carriers don't have to always be electrons. They can be a variety of different kinds of things. So in high energy physics, they can be fundamental particles. As you'll see in this class in the future, they can actually be holes, which we'll define later. And so the conventional current can scale depending on the amount of charge those charge carriers actually have. So to summarize, we can drive a current by separating charge. It is precisely the surface charge gradient that produces the electric field and thus pushes electrons around the circuit. The electric field that is in the wire points from the positively charged plate to the negatively charged plate. Makes sense because the pushes are going to be in the opposite direction due to this force law. The electron current we've defined as the number of electrons that pass a point per second. We're going to dig into the sort of microscopic properties in a new video, in one of the next videos. But there's a difference between the number of electrons that pass and the amount of charge that passes. And so we're going to keep track of those things separately because they actually have different meaning for us.